Hi everyone, Todd Gonzalez here again from Lowell Observatory. I'm here with another science challenge. For this one, we've got something for the older kids. We are going to measure the speed of light through a substance. And so I have a quartz crystal here and my green laser pointer. And something really interesting in physics here is light moves at the speed of about 300 million meters per second. But when it passes from one medium, air, to another medium, which is our quartz crystal here, it slows down. And if I have that coming in at an angle, I can actually see the light is bent, and I can use geometry and Snell's Law to figure out what that speed is. And so that's what we're going to do today, but we're going to do it with one of my favorite things. We are going to do it with Jell-O. And so you're going to want to have one of these packs of Jell-O. I used orange because orange actually shows our red laser pointer a little bit easier. This is an old laser pointer from 1991. I'm not actually going to use my green laser pointer this time, so I'm going to stick with the red laser pointer. And so we're going to need Jell-O, we'll need a laser pointer, we'll need some protractors, and if you have one of these at home, perfect. If not, have no fear, you can actually print them out and they still work. So I got a bunch that I printed out. You can even cut them out. So you can get your protractors online. The next thing you'll need to have is, well, you might not need it, but the ruler, it's just that you can draw straight lines. And if you don't have a laser pointer, I'll explain more about how you can use a flashlight as a possible light source for your Jell-O. So we're going to be using Snell's Law today. And I promise it's not going to be, the math is not going to be that complex. It's actually going to be pretty easy. So you'll need a scientific calculator and something in degree mode because we are going to use the sine function on the calculator. But basically what we're going to do today is we're going to shine a laser through Jell-O and we're going to measure the angle at which it goes into the Jell-O, and then we're going to measure the angle at which it bends inside the Jell-O. And so this first angle is called the angle of incidence. That's the angle at which the light source, the ray, comes into the substance. And then right here is called the angle of refraction. That's the angle at which it is bent when it slows down. So really cool that we can see light slowing down and bending toward normal when it goes into a more of a dense material. So with this law, we should be able to do some geometry, simple geometry, and then figure out how fast light is moving inside that Jell-O. So I'm really excited. If you are not an older student, let's say you're in elementary school and you want to try a challenge at geometry, this is perfect for you. If you're in middle school, this is also perfect. So please stay tuned. All right, so let's get started with our setup. So you could either print your protractor, or you can, if you have a protractor handy, that's also useful. I printed mine because we're going to be writing on the paper as well. And that's the wonderful thing about circles is no matter how you scale them, they're going to be pretty accurate and useful. So printing them or having a normal protractor really doesn't matter. Some things that we want to mark first before we get started. We want of course, we have our bottom line here. So this is where that laser is going to be aimed, right in the middle of this protractor. Another line that we want to kind of have ready to go is our normal line or our perpendicular line. And so I might make a line there, but it's just easy to use a ruler here and make sure that that's nice and straight. So let me get this done here. That's not very straight. There we go. So there's my perpendicular line. And the reason why I'm marking this is, one, so when I'm aiming the laser, there's somewhere to aim the laser, but also there's going to be a time where I'm going to need to bring in another protractor and get things lined up. And so these lines make it very useful later. Now, if you weren't using a printed one, and let's say you were using our normal protractor here, how you would do this to get this set up for your experiment is you want to first mark that circle there. That's where we're going to aim the laser again. Then the next thing I'm going to do is, since this moves around, there's a chance that this could get knocked, or I need to pull it away for something. So I am going to mark where that bottom line is for my measurement. And let's see here, get that one right there. And then again, I'm going to do the perpendicular line. And so now I can take this protractor away and I can start making my straight line here. It's kind of hard to see from behind the camera, but I'll do my best. So, oh gosh, that was horrible. Anyway, I'm not going to use this one, but you get the idea. You're just going to draw your lines nice and straight. And if you're not messing up like I am, there we go. And assuming that this one went to the mark here, if you had to bring this back, now you should be able to line it back up at their proper location and make your measurements. So if you're using one of these, I recommend getting a piece of scratch paper and making your lines. But since we're printing our protractor, it makes life a little bit easier since it won't move around on me. So now that we have our protractor set up, the next thing we want to do is we want to get ready with the Jell-O. And with the Jell-O, I got this box here is a 6-ounce box. It comes with the jiggler recipe on it. And so let me see if I can show you here. There's the jiggler recipe. So it's on the side. It basically makes the Jell-O a lot more firm and easy to play with when you're doing this experiment. There are lots of these recipes online, so feel free to pick your favorite one. I used orange. I feel like orange worked really well with my red laser. So you want to make your Jell-O and let it sit in the fridge, get nice and firm, and then you have your Jell-O. And here's mine. And something important about the Jell-O when you're cutting it out, you want to make this edge here and this edge here as straight as possible, because when the laser comes in, if there's a bunch of waves and it's all messed up from cutting it or pulling it out of the pan, it's going to make the light kind of bend in all kinds of different ways. But we want it to be as straight as possible. And I think this might be the straightest Jell-O I've cut. It takes a little bit of trial and error. You don't want to try to cut a big old square, because then you rip into a lot more of your Jell-O than if you did a little square. Then I have plenty extra just in case I mess up. I put it on a piece of wax paper here, and that's because Jell-O has a little bit of moisture to it, and if I put it right on the paper, it would start to soak into the paper. So I put it on this wax strip here so that I could move it accordingly. Now, when I line up my Jell-O cube here, I'm going to line up the edge right with that. You see the crosshairs here, this perpendicular normal line, and then this what we consider the bottom of the protractor. This isn't the bottom, because look where the degrees stop. We want to be right where the measurements stop, and so I'm going to move my Jell-O right up in line there. And so now the flat edge of my Jell-O is up against my protractor for measurement. So I've got that in place. My Jell-O is good. My protractor is good. I've got my measurements down. Next thing I want to do is get my laser pointer ready. Now this is where things get kind of tough, because if you're using a cap, one of those typical little laser pens you put on a keychain, you might need to tape the button on, because you don't want to be messing with it while you're taking your measurements. Luckily for me, I have a excuse me, a 1991 laser, which I'll show you here in a little bit. I've got it set up for now, but I'm going to go ahead and flip that on. All right, and so the next thing I want to do with this laser pointer is I want to get it so it's aimed right at the center here. Let me move the Jell-O out of the way. I want the laser to come right to this point. And so with my JellO moved up to the edge, I know that my laser is a little off. You can see it's a little bit to the left there. And so I'm going to make some adjustments so that my laser is right in the center of the protractor. Now, once I have my laser kind of set, I can always adjust the paper instead of moving the laser around, because it gets kind of tough with when you move the laser itself around, the laser pointer. And so here we go. I think this is actually pretty good. The laser's lined right up over the dot and it's hitting the side here. Now, I wish I could, I'm going to try to move the laser here a little bit so that you can see, there we go, where it is. So here's my laser point right here. And what I want to do is I want to try to figure out if I can get it lined up to one of these. Now, to make it easier on myself, I'm going to go by tens here. So from 90, here's 10 degrees, here's 20 degrees, here's 30. It'd be a lot easier if I could just pick something that's divisible by 10 instead of trying to set my laser up for something in between. It just makes it a lot easier if I can line it up on one of these larger hash marks here so I can do my measurement. So that's what I'm going to try to do here. And I'm going to go ahead and make sure that my laser is still lined up in the center. And it might be one of those things where, you know what, I might have to move the paper around instead of the laser pointer. And another trick that I've learned is you can take the tip of your pencil and figure out where it is on your protractor. And so right now it's pretty close. I'm going to keep it close to 140 here. Let me go ahead and move this a little bit more. My finger out of the way. All right. There we go. So you can see that the laser is pointing right over this 140 mark right here and coming straight down to the center here. Now this is 140 on the protractor, but really it's 10, 20, 30, 40, 50 degrees. So now that I've got it there, let me speak a little bit about laser pointers. If you don't have a laser pointer, something else that's worked that just needs to be a lot closer is I took a flashlight, and as you can see, I've taped so that only a slit of light would come through. Let me go ahead and turn it on here. That doesn't really work in the camera, but only a slit would come through. And basically I could do the same thing with my JellO, but the flashlight has to be a lot closer and you have to get pretty creative. So you can do it with a flashlight, but I recommend using a laser pointer if you have one. Now laser pointers you can get pretty cheap. Dollar store, I've seen them at the dollar store, and you can get them on Amazon pretty cheap. So most people have them around because their pets love to play with them. So I've got my laser pretty much set up. So the next thing I'm going to do is I'm going to just make a mark at where I have my laser. And so I'm just going to, just a reminder basically, oh, I'm at the 140 mark here, or 50 degrees. And the next thing gets a little bit tricky. So you can see that the laser's coming in at 50 degrees, but notice that it's bent. It's actually closer to it bent closer to the normal line here. And what I want to do is I want to find where that laser hits or starts to come out of the JellO. And so I believe I have it right here. And so the problem with my paper here is it's a little too long, this wax paper, and so I'm not able to really make a great mark on the paper itself. So I'm just going to kind of work with it here. Let's see. And I don't want to make a mark of the laser coming out this way because it bent again coming out. I want to mark it where it's hitting this back wall inside the JellO. So it's basically right here. And if I can get my pencil underneath here, see, I probably would have made this a lot shorter. There we go. That wasn't so hard to do. I can see where the laser is on the paper as my pencil moves under it. So I've got my mark there now too. So I've just done one trial. So I know that this is 50 degrees, but now comes the part where I have to measure this. So now that I've got this all marked up, I can move the Jell-O out of the way now. There's nothing wrong with that. And there's my mark right here. And so what I want to do is I'm going to take my ruler. I can even take my protractor edge here as a ruler, because all I need is a straight edge. And I'm going to go from this dot. Remember, that's the center of where the laser was pointing. And I'm going to go ahead and trace my line. That's horrible. There we go. And I'm going to take it a little long, just so my protractor has something to measure. Now, whether you're using one of these, you can line it up with those lines again, just like that. So the center is right underneath there. And so I can measure my degrees here, or if you're using strictly paper, I cut one out. And so that's another way we could do it. And you can measure. Now, if you had your lines out a little bit further, you'd be able to tell as you're moving the paper above the other protractor. So we're just going to use our clear one for now. So we've got our first measurement, and I'm going to line this up. So there we go. So this line is still on 90 degrees. And so what we have here, if we say, okay, this is 10, 20, 30, and it's just shy of 34. So I'd say 33.5. So I'm going to make a mark there, 33.5. So now I've got that measured. And so what I'd want to do from here is, now that I have that measured and I kind of have an idea, if I'm going to do this multiple times, I'm going to make sure I want to distinguish these two here. So maybe I would label this one as, I don't know, we'll say it's trial 1. And I might put a 1 under here, just to kind of give me some other idea that, okay, this one was one shot. So if I move my Jell-O back over and align it back up, and then I move my laser pointer and try a different angle, the idea here is that this isn't a really perfect way of measuring it. So if I can get multiple trials, I can get the average of the number I'm looking for. So we can actually have fun with this right now while we've got our marks there. You can see that the light was coming in and it bent toward normal. So light is actually slowing down in our Jell-O. We're actually seeing that with our own eyes, and that's really, really cool. And in a little bit of time here, we're going to actually measure that. So I'm going to shut off my laser pointer. And so now that I have my first measurement, I have 50 degrees here and 33.5 degrees here. Just again, as a reminder, I'm measuring the angle from this normal line here. And so I'm not going to put 140. I'm going to just measure, okay, there's 10, 20, 30, 40, 50. And the same over here. I was going to do the same over there. If I put the protractor there, I'm measuring from the perpendicular, from the 90 degree. I'm not going to say, oh, this is 63. No, I'm just going to go 10, 20, 30, and 33.5 is kind of how I see it there. And so now it's time to plug these two things into my equation. So my angle of incidence, and I'm just going to write right on here. That's another great thing of having a protractor that's printed. You have yourself some scratch paper here. My angle of incidence is 50 degrees, and my angle of refraction is 33.5 degrees. And so there I go. I have my first trial. This is trial 1. And now all I have to do is plug it into my equation. And if I'm going to find the index of refraction for Jell-O, I know that after doing all of my algebraic moving around, I know that I'm going to need to take the sine of my angle of incidence, so 50, and I'm going to have to divide that by my sine of my angle of refraction, which is 33.5. And that is going to give me my incidence, or sorry, my index of refraction for Jell-O. And so, of course, there could have been something I've done wrong, and so I'm going to want to compare that to the table I sent in the lesson plan. Does this number make sense? Is it, you know, a vacuum is 1, air is pretty much 1 too. If it's 1, then I can pretty much assume that, oh, no way, this can't be as dense as air. It's got to be more dense, so it can't really be 1. But it also can't be 2. 2.4 is a diamond, so this number better not be 2.4 because I know that this is not as dense as a diamond. So it's got to go in between what I would assume water and sugar solution would be. So you can look on that table, and water, you know, is 1.3 if you're looking at the table. So I know that this isn't just water. There's some sugar in there too. So my hypothesis is I believe that this should show a number in between 1.3 and maybe something close to 1.6. So when I do my math, I have some way to check. Another way to also check when you're doing your laser to make sure that you have a flat side is one of the great things about the angle, or sorry, the law of reflection is whatever angle the light goes in. You see this is a reflection, so this is the law of reflection. Whatever angle it goes in, that's the angle it should go out as well. So if I have 50 degrees here, I should be able to measure this, and it should say 50 degrees over here as well. So there should be 50 degrees when it comes out when it's reflected. So that's just one way to check to see if your Jell-O is in good shape and it's as straight as you can make it. So now that we have these numbers, I'm going to go ahead and calculate those and see how I did. Of course, I'm going to want to do this multiple times, but I should get an average of whatever this number is, and I'll be back in a little bit and show you what those numbers mean. All right, so now we're going to revisit Snell's Law. So we've done our trials. I've only done one trial in this example, but hopefully we've done a few trials. So I've got my angle of incidence, which was 50, and I have my angle of refraction, which is 33.5. So remember, this is the angle of refraction. That was the measuring the bending of light in the Jell-O, and this was where I set my laser pointer. So coming back to this, it's pretty easy to see where I fill in those numbers. I got my angle of incidence right here, and so I'm going to erase that and erase this, and my angle of incidence was 50. So I'm going to put 50 in there, and then my angle of refraction was 33.5. So there we go. So now comes I like this part, but you have to try to figure out, how do I move this equation around? Because I want to know the index of refraction for Jell-O. So how do I get this by itself? I want to get rid of this, but I want this by itself because I want to know what our index of refraction is for Jell-O. So if you want to pause the video and do it yourself without me working through it, that's great. But I'm going to go ahead and get started. So the first thing I'm going to do is I'm going to divide both sides by my sine of my index of refraction here. So I'm going to just do it in yellow here, 33.5. I'm going to do that to both sides. All right, so what happens here is these cancel out because they're the same. And what I have left is my sine of 50 and over my sine of 33.5. And then I have the index of refraction for Jell-O by itself. So I still need to know what air is, and I've got my my lovely table up here, but I don't have air up there. And that's because I wanted to tell you what air was. So looking at this, what the index of refraction is a ratio. It's the speed of light in a vacuum divided by the speed of light in the substance or medium that you're measuring. So basically in a vacuum, light is moving at its speed, 300 million meters per second. And just to give you an idea what a meter is, so this is my 36 inch measuring device here, but if you add 3 more inches, that is about a meter right here. So imagine 300 million of these. Light can travel that distance in 1 second. And so when it passes through our Jell-O though, it slows down. And so vacuum has an index of 1, an index of refraction of 1. Water is 1.33. Sugar is 1.5. And diamond is 2.4. Basically all that means is light in a vacuum travels 1.33 times quicker in a vacuum than it does in water. In a vacuum, it's the same speed, so it's 1. In a diamond, light travels 2.4 times faster in a vacuum than it does inside the diamond. So we want to figure that out for Jell-O. Luckily for you, the air, I know the one for air, and air is pretty close to 1. To draw it out for you, air is 1.00004, if I can fit it in there. So it's pretty much 1. So, you know, for our purposes, I'm going to go ahead and just leave it as 1. If I was a scientist that needed to know to the decimal how fast light's moving in air, I would probably add those other significant figures. But for our purposes, we're just going to use 1. And I've already done this math, and I know that our index of refraction for the one trial that I've done is 1.39. So there's no units to that. Now, here's where I check myself. Okay, does this make sense? Does it make sense compared to all the other ones there? Well, I know that Jell-O is made out of water, it's made out of sugar, it's made out of glycerin, so I know that it shouldn't be 1. It's not, Jell-O is not so rare, or it's not a vacuum, so there's no way that it should be 1. And it's not quite as dense as diamond, so there's no way it should be 2.4. So it should be in between what I think would be water and maybe sugar. Is this number kind of making sense to me? And yes, this number does make sense. Is it accurate? I don't know. I would need to do a few more trials. I don't know if I messed up. I don't know if this is going to be closer to 1.5. So that's where these other trials come in. So now that I kind of have my number, and we're just going to go on without the trials here. I have my number. Now, I need to figure out the speed of light in the Jell-O. So this is my index of refraction for Jell-O. Here is what the index of refraction basically means. It's a ratio between the speed of light in a vacuum and the speed of light in a Jell-O. So what I'm going to do is I need to get the speed of light of a Jell-O by itself. And so, all right, so there's 2 numbers that I know for sure, but I need to rearrange this equation so that speed of light of a Jell-O is by itself. So the numbers I know, I do know what n is. It's up here, 1.39. So I'm just going to go ahead and change that to 1.39. I know what the speed of light in a vacuum is. We just talked about that was 300 million meters per second. I'll put meters per second there. What we don't know is the speed of light of a Jell-O, and I'm just going to go ahead and put Jell-O here just to kind of make it easier for me. And so what I need to do is I need to rearrange this so that I get Jell-O by itself and I can solve for what the speed of light in a Jell-O is. So what I'm going to do is I'm going to multiply both sides by Jell-O. There we go. And so these guys cancel out. And so what I got now is I've got the speed of light of a Jell-O times my index of refraction of Jell-O and the speed of light in a vacuum. So I need to do one more step. I need to move this over here. And so what I'm going to do is I'm going to divide each side by 1.39. That's going to cancel out or become 1. And what I end up having is my speed of light in a Jell-O. Speed of Jell-O, there we go, of light. And all I have to do is this simple math problem here with my calculator. Divide the speed of light in a vacuum by my index of refraction for Jell-O, and it should pump out what the speed of light is in my Jell-O. I'm not going to do that because I want to see your examples, your index of refractions, your indices of refractions, your speeds of light. So I'm excited to see what you guys come up with. Have fun, and like always with the Jell-O, once you're done with it, as long as you've washed your hands, you can eat it. All right, have a good one.